Well, hello, I'm Christopher Ness. I'm the Maudslay-Butler Research Fellow at Pembroke College, and I work in the chemical engineering department. The Maudsleys have been a prominent family of British engineers for the past 2 centuries or more, and they've sponsored a fellowship here at Pembroke since the 1970s, and many previous Maudslay Fellows are still around and have positions throughout the university. So my research involves the flow properties of materials. So I'm particularly interested in how materials deform, how they flow, and how they respond when we apply stresses to them. And my focus is on suspensions, which are mixtures of solid particles in a liquid. So dilute suspensions behave a lot like normal liquids in that they flow. But when we add more and more solid particles, the viscosity increases. They become much more viscous, and eventually at a certain concentration they can start to jam or solidify, at which point they no longer flow. A sort of very popular example of this behavior is a cornflower suspension. So the cornflower suspension is a kind of fun example of suspension behavior that's often used at science fairs or public engagement events or school demonstrations and so on, where you often see school kids, people running across pools of cornstarch. And it's a very dramatic physical property of the material, but what surprises people is that the underlying physics is very poorly understood, and actually a lot of active research is going on precisely to try and explain what's going on with the material. And it's not just for the sake of fun, it's relevant to many applications. So for example, suspensions used in industry include ceramics, cement, oil drilling fluids, and so on. And if we can understand exactly how the particles in the liquid interact at a micro scale, then we can design materials better and sort of study how to make materials flow better in order to reduce the energy costs of many processes across industry. In order to understand the generic behavior of suspensions and how they deform, we built a scaled up version of this cornstarch experiment. So instead of using flour particles, which are around about 1 micron in size, that's about 1,000th of a millimeter, we use these plastic particles, which are 1 centimeter in size. Now, the good thing about these is that they're birefringent, and that means if we shine polarized light through them and then apply a force, we can see beautiful stress patterns on them. And then if we take hundreds and hundreds of these particles and create an assembly, we can see exactly how the forces flow through the material. We then build a 1 meter diameter mixing bowl and fill it with these particles and a liquid. And then when we stir the suspension, we can see intermittent flashes of forces and also persistent contacts between the particles. So with this unique device, we can understand exactly how the torque that we applied to the stirring wheel is distributed between the particles and the liquid. And once we know that, it gives us a lot of information about how to design these materials. For example, if we focus our design efforts on the particles themselves or on the properties of the liquid. So this experiment just represents one aspect of the research I do. The general theme of overall of my research is to understand how microscale interactions, so for example the interactions between the particles, can influence the overall bulk behavior of the material.